Hi everybody, welcome back. So in this part, we're going to start out by checking for shorted output transistors, because if you remember in part 1, and I mentioned this also in part 2, that we had full DC voltage on, the whole rail voltage, power supply voltage on one of the speaker terminals. I forget it was which channel. And it actually is possible to check the output transistors for shorts in circuit without removing them. Now you can do this a couple of ways. You can use an old analog volt ohm meter, which will work just fine. And those are typically more low impedance type meters. Or you could use a DMM and it should still be able to test it. So we're going to use the DMM. I could also get out my voltmeter, but it's all the same thing. So the idea is if you read from the collector to the emitter of these transistors, it should read higher ohms, like a couple hundred ohms or something. If it reads closer to an ohm or less than 10 ohms, then one of the transistors in this line will be shorted, okay, when you do that. And you can reverse the probes and check it both ways and just make sure, that that's how it works. Now, the thing is, the power supply is connected to this. So you are going to have some of the influence of these capacitors on that when you read it, even though they're fully discharged and the thing's unplugged. You want everything to be discharged and unplugged when you do this. But it would probably be a better test if you took the time to remove the power lead from this. But again, we'll know what we're looking at. So I'm going to go to ohms, and I'm going to start on this side and kind of move my way over. So again, if you want to know which pins are which on the transistors, well, you can tell by the things that are wired to them. So like the collector is always going to be the case of the transistor. So here's a TO3 transistor. I picked this one on purpose because it has the elements marked. See that? And if you notice, there's only 2 pins, even though it's a 3-terminal, device. That third terminal is the case of the transistor, for those of you who don't know. So this would be the collector. And then if you hold it, you'll see there's a short dimension and a long dimension. If you hold it with the short dimension down, your emitter would be on the left, your collector will be, emitter will be on the left, the base will be on the right, and then this is your collector. So emitter, base, collector. Keeping that in mind, here's the short dimension here. So that means that this is going to be the collector, which is the case. See, it's connected to the screw terminal. I probably should go a little bit closer with you on the camera. Be patient, some of you, because there are some folks who aren't familiar with this. I'm showing them. So here's the case, which would be the collector. So this is the collector rail. The base is going to be this one here. Okay, so here's the short dimension here. So your base is going to be here on the right. And you can see it has that ferrite bead on it. That's how you could tell this. The base is always the one in these amps with the ferrite beads on them. And then the emitter is going to be the one with these emitter resistors on them. So we want to measure from the collector to the emitter to look, because that's typically how these short on these units. So let's go back this way. Bring everything into focus here in field. So I'm going to go from collector rail to the emitter, and you can see it's about 300 ohms, and it's climbing because I'm reading through that capacitor there. But the good news is there's no shorts. If it was shorted out, that would be completely would read low ohms. So let's go to this side and do the same thing. And see, that's reading almost open too. Now remember, these are 330 milliohm resistors, so they're less than 1 ohm. So, and you notice how they're all tied together. So all of these transistors are tied together to one another through these low resistance resistors. So if I go from here to here, it's only going to read about an ohm. See that? 0.8 ohms. So basically, if one of them shorted anywhere in the line, it'll find it, with the exception of the driver transistor. So we want to check it over here, and you can see it's good also. No shorts. And the driver transistor on this side, check it, and it's good. So this side is good by the looks of it. All right, so now let's go to this one. So we'll go from the collector rail to one of the emitters. And I have a short, look, 1 ohm. Do you see that? 1.16 ohms. If I flip the leads around, same thing, 1.16 ohms. So somewhere in this line we have a shorted transistor. If I go to the emitter of this one, this is the driver, you can see it's not shorted. It's 194 ohms, so that one's not shorted. The driver is still good, at least there. And emitter to base, I mean collector to base, that's very low ohms. And emitter to base, we do not have any emitter to base shorts. You see that? 10 ohms that way. Oh yeah, 10 ohms, okay. I just wasn't on it good. So we may have a bad, we definitely have a bad transistor in here. So let's see if this side also went out. So I'm going to go from here to another emitter, another dead short. Look at that. So these ones are bad too. So this whole side will need to be replaced. And actually, since these are the vintage transistors in here, the old Motorola's, I will replace the entire set with modern ones. And they are the correct ones. What are they? MJ 15025 and 15026 or something like that. I'll put it up on the screen here. Just so you know, there are two different types of outputs on these. Now the one that I show you in the schematic, see this is the full complementary one. So it has NPN transistors on one side and it has PNP transistors on the other side. So it's half and half. The ones with the quasi-complementary, and I don't know if I have a diagram of that. Let me see if one of these pages shows it. Let's see here. Yes. And you can see it even says Series 2, so it has nothing to do with what series it is. This one's a quasi-complementary. So you have to be aware of that when you go to work on one of these or one of the 400s. It could be a full complementary or it could be a quasi-complementary. If it's quasi-complementary, all of the transistors are NPNs. If it's a full complementary, half will be NPN, the other half will be PNP. Again, obvious to some of you who know this stuff, but those of you who are not familiar with this, be aware of that, and you want to look and check for what one you have. The easiest way to check it is to just take the cover off the back. If the numbers on the two sets of transistors are different here and here, and then different here and here, you know you have the full complementary. If they're all the same transistor all the way across the board, you have the quasi-complementary, which is the older style. If you recall, the phase linear 400 that I did on the last video was a quasi-complementary. It had all NPN transistors. And they were all good, so I didn't touch them. I left them alone. Okay, before we start getting into this, what I'm going to do, and I'm saying this to remind myself when I edit the video, I'm going to put up a copy of this schematic, and if I have a couple other pages, I'll put them up on the screen, and you can pause the video and do a screen capture And then if you want to save them to a file on your computer or print them out to have a printed version, and then you can follow along as I'm doing this. Another thing I found in the service manual, I looked it up here, I printed it out. Here's the wiring diagram for 220 volt versus 100 or 240 versus 120 on this. And I explained this on the power supply, part 2 video, but here's the actual page showing what I showed you. And it actually has the color codes for the wires, so you can actually follow along, what colors belong where if you're going to wire this for one, mains or the other. So there you go. Here's the layout of the board. And like I said, the other big schematic I'll actually put the file up on the screen so you could see it. But you can screen capture this as well if you want to. And I'll be following along with that. So here's those two transistors that look cooked. And if I look on my schematic, I'm going to put this on ohms. If I look on the diagram, the location diagram, those appear to be R108 and R208, and they are 3.9K. So I can see the 3, there's the orange, but the white is missing. It's burned up. So you can see it's 3.7K, so they still are intact, but you can tell they got really, really hot. So they haven't burned up, but you can tell they got hot. So let's look on the schematic and see. I'm really interested in knowing what that 3.9K is. R108 is right here, and it's 3.9K half watt. So you can follow along on your little printout that you did, I hope. And these are what set up your overcurrent or your power limiter circuit. You can see that these two transistors. And so if you're putting full DC rail across this and through here, that's probably what's causing it to overheat, because that's going right to ground. It's 3.9K, but if you put full rail voltage across that, well, let's figure it out. So accounting for about a 1 volt drop on that diode there, you would have, with the rail, if this were shorted, you'd have somewhere around 103 volts divided by 3,900 ohms. Gives you 26 milliamps times 103 volts, 2.7 watts across a half watt resistor. And that's why it got really hot. So that would explain things, wouldn't it? See, I like doing exercises like that because it helps you to understand how a circuit works, when things fail, why they fail. There's a lot of videos out there where people just go through and they wildly check everything, and if it's shorted, they replace it and move on. But they never really understand how the circuit works, nor do they care. Well, that is an effective way to make a repair on something. It's not a very effective way to understand how a circuit works, though. If you want to get better at electronics and circuit theory, do things like that. This is a hobby. Take your time and go through and learn. That's how you get good at this stuff. If you don't do that, you'll never get any better. And maybe you don't want to get any better. Maybe you just want to fix it so you can listen to your music. That's cool. I'm not your channel for that, though. I'm too inquisitive for this. I'm too interested in how it works to just rush through it. Okay, so let's take a look at a few other things in here. So in both the left and right channel, this resistor was overheated, but this one was not, because there's R112 and R212. That would be this one here, and you can see it's perfect, and it's reading okay, but you can tell it did not get hot. So the transistor that's connected to that would be Q102. All right, and Q102 happens to be this transistor down here. So we're going to look at that one. And I'm going to go to diode check. And let's see, emitter, base, collector. So let's put the base here. That reads really low, but it might, let's flip it the other way. There it is. Okay, so it's a NPN. See, that reads low resistance in both directions. See that? There's no difference between the emitter and base. See there? So there's a problem probably with the emitter to base on that side. Let's look at this one here. Same thing. I'm trying to stay out of the way so we can see with the camera. It's reading the same, and probably in both directions. Yes, it is. And then if we go to this side, so that's reading the same, so maybe they are okay. And this one is a PNP. Same kind of thing. So that has to do, you're looking at in circuit. That's because it's in circuit. That's why you're reading that 170 millivolt drop instead of a regular diode drop. But most likely these transistors are good. I'm going to say they're good. Let's go to this one. That's good. That's good. No shorts. And I did not check emitter collector for shorts. I don't see any. So no emitter collector shorts there. And let's check this one. So these are PNP transistors also. All right. So that would be Q103, which would be, that would be the emitter follower that is straight out of the op amp. I don't think anything's damaged this far back. If we're going to find a bad transistor, it's probably going to be one of these drivers. And then Q104 would be, or 106, I think it is. 106 is this one right here. I'm sorry, right there, see it? And that one might be bad. I don't know. We'll have to see. So to get to those, you have to flip this over. And let's check it out. Nope, that one seems to be and I don't remember, because this one has kind of, I think the base is, yeah, the base is the one on the left here. So that one's good. Let's go to this one. Base, once again, is good. And this is an NPN. Well, I'm not getting on there good. Okay, so those are good. Let's check these ones here. And I forget which ones are the PNPs and which ones are the NPNs, but okay, so that is the NPN. No problems there. And this is going to be the PNP. Or is it? That one's reading open, unless I'm not getting on it good. I'm getting a junction there. Okay, so this one has a different pin out. And it's open there. Okay, so let's go to this side and make sure it's the same. And that reads weird. See that? So that could be something down the road though from the, from the outputs or something. And then let's check this one. Okay, that one's good. And again, I think we're reading possibly across something there. Maybe not. Yeah, I'm reading across a capacitor. So if I flip these leads around, it'll read differently. Yeah, no, it doesn't. Okay, so this could be, possibly could be a leaky transistor. We don't know. Remember, this was the good side, so there may be something wacky going on with the transistor here. So these are questionable. All this stuff up here, fortunately, is, I'm going to say, good. Just as simple as that. We've just troubleshot this. Now, of course, we can go through and verify our, all of the resistors. Like these ones here. It's a 5K. And this is a 7. Yeah, there's weirdness on those. Those might be open. Let's check those out. That would be the 7.5K resistors, R101 and R201. Those should be 7.5K. And this one, in fact, is, if I can get on it right, that's reading 5K, but I might not be on it good. 5.4. What's this one say? $8K. See, that's off. So these are both bad. These are probably bad. So, and that would make sense because once again, let's look at R101 is going to be R101. Let me make sure I got this right. Yeah. So you have R1 is here. R101, yeah, right here. 7.5K, 2 watt. So it's bad. Okay, so I have gone through and dug out most of the components I'm going to need to rebuild this thing, with the exception of the big transistors, which I had to order, like I said. And I'm probably going to replace those 330 milliohm resistors. They're 2 watt. I think they're 2 watt. Yeah, 2 watt. With these ones, which are a much better quality resistor. The thing I don't like about the ones that are in there, they're fine, and I'm sure they're perfect. Those Allen Bradley type carbon comp resistors are usually pretty good. But what I don't like about them is their failure mode. And what I mean by that is when these fail, they don't just burn open and just open, like a metal film or a metal oxide resistor would do. They'll actually burn. And I really don't want these burning if a transistor shorts out into its load and doesn't happen to blow the fuse here. So we're going to replace that. This is a huge mess. You can see from these speaker terminals. I don't know if I'm going to just wholesale replace the speaker terminals, because the ones that are in there are okay, or what I'm going to do, but I'm going to have to do something about that because they really messed it up with all this. So these wires may need to be replaced totally, because I don't know if they'll reach over here anymore because they cut them. So I may have to reroute all new wires. And it's kind of strange because this channel, if you look at the diameter of this wire, the gauge of this wire, versus the white, this channel, this is actually a thinner wire, even though it's a longer run. Do these things matter a whole lot? Not a whole lot, but still, it's death by 1,000 cuts. The more things you can get right, it'll add up to better performance overall. At least that's my opinion on it. So that's my plan. And I'll just kind of go in and out with you as I progress through this, and we'll see where this ends up. Okay, so we have this part of it done, as you can see. And what I basically did was installed this board, and this is similar to the one I did on the 400, only instead of having an integrated circuit, this one uses all discrete components. It'll be a little bit easier to fix if it breaks, because that chip might become hard to get one day. And these relays are pretty stout relays. They're rated at 30 amps at 250 volts AC. Again, it runs on mains power, so it's connected. I have it connected right across this convenience outlet, and it is a switched terminal, so when you switch the power on, this board kicks on. Just like on the 400, we have the Zobel network, which I rebuilt. I just used new resistor and capacitor, same value. And you can see the snubber that goes to the speakers. And that's right there. And this is the 22 turns of number 18 solid copper that's in parallel with this 10 ohm 2 watt resistor. This is actually a 10 ohm. What are these rated at? 10 ohms at, I think these are 3 watt. No, they're 2 watt. 2 watt. Let's see here. Sorry, 10 ohm 5 watt. So that's that. And there's a 10 ohm 5 watt inside here. And these are your 22 turns of that wire. So these are the snubbers, and you can see they just go directly into the input of the board, come out of the output of the board, and goes to the terminals. And I did have to replace the terminals because the old ones were just so boogered up from being soldered on all the stuff. I had to really clean that up. They had such a bubblegum mess there. And then I had to run new primary or power speaker leads from the amplifier's outputs. So here's your left channel and your right channel. Right there and here, and they kind of snake their way up into here, and that's where it enters in and then comes out of the snubber and goes into here and so forth. So everything's good to go there. Now the next thing I'm going to do now, and so remember we were talking about bypassing the big filter capacitors here, and I kind of explained to some of you why you want to put your bypass caps. You don't want them on the big caps. You want them to be as close to the control element as possible. Well, lo and behold, we're not going to have to do that. If you look on the schematic, and I don't know if the old quasi-complementary has this, I suspect it does, but you can see these 330 nanofarad caps. Look at that. They're right down here. They go right to ground, and they are very close to the control element. So the bypass capacitors are already installed by the factory. These guys knew what they were doing. Now the big challenge is I want to replace these carbon comp resistors with proper flame-proof resistors that'll just open without burning. If these ever shorted out, drew really heavy current, they will burn. I really don't want that. So we're going to replace these, and getting them off of the transistor terminals is pretty easy because they didn't wrap them around the terminal or anything. The big mess is this terminal here and here and here and here. So I'll just have to very carefully, with a really strong desoldering pump, clean this off as best as possible and just take them all out and put the new ones in. All right, well, 2 hours later, there it is. And I ended up, since I was in there, I took these out and I replaced them with some 1 microfarad 250 volt. The main reason is on a few occasions I've seen these green capacitors dry out and then they crack, especially across the top. But these ones are still somewhat pliable, so they probably would have lasted a lot longer. But while I'm in there, I might as well do it. So that's what I did. Resistors all are in the same position that the old ones were in. I think the wire placement on these is very important, especially, you know, when you're talking about the thing oscillating and so forth. So I made sure I got everything in the same position that the old ones were in. So we're ready to move on to the actual circuit board, and that'll be the next step, and that should be finishing it up, and we'll be ready for testing. All right, we are on to the circuit board, and before I do that, I'm going to remove these bias transistors. They are kind of known to be a point of failure. So what I'm going to do is, like I did on the 400, I'm going to replace them. I'm going to use these right here, which is the Toshiba TTC004B. All right, and here are our new bias transistors. And I do like these ones better than the originals. In addition to being able to handle, you know, more power, so they won't be as prone to failure, they also will track more rapidly. In other words, the way these couple to the heatsink, they actually will, when you apply heat to them, the VBE will move more rapidly, and it will move over a little bit greater range. In other words, it doesn't take quite as big of a change in temperature to get a change in VBE on this. Now you might think, well, you're messing with the bias tracking. Well, you are. But in this instance, because this is, you know, so far away from the transistors and everything, that's actually going to be a little bit of an advantage in this. If it works out the way it did on the Model 400, I think this is actually, the bias is going to be really solid on these. So we'll find out when we get everything all kind of tweaked in and calibrated, you know, tested. But I think this is going to be actually an improvement to the bias circuit. Okay, waiting for the alcohol to dry because I used some isopropyl to clean off the flux. But you can see the new wires are attached and the new transistors are fixed in their place. And now we can move on to the components on the board. Okay, let's start removing these chips here, and let's see if we can get them to come out without lifting any tracks. This is really delicate work here on these, because these traces will just lift off the board if you look at them crooked. Okay. I'm not applying any pressure at all on it. There goes number one. All right, let's do the next one. And there we go. There's our two chips. Now my question is, are these both good? I'm going to say they are. Okay, I have our little tester here. Plug this into the single slot. These are just handy little boards. You can get them on eBay or whatever. They're cheap. All they do is just apply a signal, kind of like a voltage follower, I think, to these to make sure that they're working, and it's a go, no-go test. So you can see the yellow light lights up. That means the op amp is good. It doesn't tell you anything about the specs. All it does is tell you that the op amp can pass a signal. And that's really about all it does. But that's usually good enough. I mean, if it'll pass a signal, usually it means it's okay. So I'll turn that one on. And it is good. So there you have it. So these are single op amps, meaning there's only one op amp circuit inside this little case. You can also, they also make these 8-pin chips that have 2 op amps in them. And in that case, you would put it in this socket for the dual. So like the LM358, the TL072 versus the TL071. And the NE5532 would be here, whereas the 5534, which is a single op amp, would be in this socket. And then there's even a ones for the quad chips, you know, the ones that are 16 pin or 14 pin, whatever, I forget. Just a cool little thing to have. They're cheap. They're little. You can buy them as a kit and build them. I bought this one pre-built. They're very inexpensive. So there you have it. I'm going to prepare these pads to put some sockets on there. And this, you have to be very careful if you do this. This is optional, but you have to be very careful or you will lift the trace right off the board. You don't want to apply too much heat or leave this on for too long. But I just want to kind of clean these pads off for the moment. Get all the stuff off of them. It'll make it a little bit easier to put the sockets in there. What you don't want is if there's even just a little tiny bit of solder overhanging these little holes, what'll happen is when you go to push the socket through there or push the new chip through there, it'll catch on that and it'll push that trace right off the board. So I'm kind of paranoid about that, so it's worth going the little bit of extra effort. Now for these, I'm going to use very high quality circular sockets. In other words, they have the round holes instead of the, you know, the flat ones. These are pretty good quality, and they'll hold the pins really well, and you can see how sturdy they are, so they should be good. Now some folks might get the argument, oh, you put a socket, you're putting something in the audio path, you know. Okay, well, you can direct solder your parts on if you want. I just don't like doing that with these, especially if we decide we want to try a different op amp, which I may do. And now I'm going to get a little bit of alcohol. I'm just going to clean the flux off of here. And again, very, very careful. We're just going to clean these pads off hopefully without lifting them. I mean, it is repairable, but if we don't have to, I don't want to. There we go. That looks a lot nicer. You get the flux off of there and everything. Okay, as you can see, before I removed those chips, I took one of those paint markers and I put a little dot on the side of where the notch would be for the chip, because this is going to be pin 1 up here, and it goes 1, 2, 3, 4, 5, 6, 7, 8, kind of like counterclockwise. So you just don't want to forget and put the chip in backward. That would be unpleasant. So that'll go in like that. The other one will go in like this, and these are not going to stay in, so I'm going to have to tape them down with something. So I'll take a little piece of tape, tape them down, and then we can flip it over and solder it in. Just kind of do something like this. Who cares how it looks, just so it works. Okay, and those are in there nice and tight, and they're flush against the board. So we'll get our iron here, and we're just going to very easily put this on there. And the idea is get on and off of here quickly so you don't lift the traces. This whole board is kind of like that. Some of the newer boards, you know, like on some of the later 70s equipment and 80s equipment, well, 70s for sure, the boards are a lot better quality. And I should really put my smoke extractor in there so I don't get smoke on the lens here. I will do that from now on. But anyway, there it is. After we put that on, we'll get a little bit of isopropyl and just clean the flux once again. And that's much better. And now we don't have to worry about if we want to replace a chip or something. We don't have to worry about that. Now, since that is on there like that, I want to go in now and I want to tack in these two resistors, or these two capacitors here, these 0.1s. And those ones are going to go from pins 4 and pin 7 to ground. So we're going to have to find a ground, just like we did on the 400. So if you saw that, and we're going to go ahead and I might even put a little bit better one in there with some leads that'll fit. Let me see what I got. All right, so we're all done here. Got these all in place, have the little bypass or the feedback cap put in. Okay, it's the next day, everything is dried, and I think what I'm going to do is I'm going to tackle this power supply over here for the preamp, or for the input stage. Get rid of this mess and get that all working, replace those Zener diodes, and kind of clean some of that up. And I'll probably do the transistors last because they're going to, I just want to deal with that. I'll kind of work my way from the front end to the back end of this board. So let's do this. I have the correct resistors for that, which are these 7.5K. They call for a 5 watt. These are 7 watt. They're actually really good resistors. And the other thing is, you really shouldn't mount 1 watt Zener diodes like this on the board. That's a big no-no. You want to bring them up off the board. The leads themselves provide some of the heat sink to allow them to handle 1 watt, or to dissipate 1 watt. A lot of people don't realize that, but when you cut the leads short and when you put the diode close to the board where you can't get airflow, you actually reduce the maximum amount of dissipation power that it can dissipate in heat. So you want to kind of raise them up. So we're going to do that, and as soon as I finish that up, I'll be back. Okay, where was I? So we got all the resistors replaced that needed to be replaced. I replaced all these little 1N4148s. There's a whole bunch of them on the board. They all tested kind of all over the place with their forward voltage. So some of them might have been getting tired, you know what I mean? So I replaced those. These tested out good. I still need to replace these and the 2 pots. And I have to measure these after I take them out so I can set the new ones the same way. And then these 4 are going to get replaced. And what I'm going to replace them with is, for the PNP, I'm going to replace it with a KSA 1381. And for the NPN, if I have one here, I'm going to use, if I can find one, there we go, a KSC 3503. And those are complementary pairs. And they are much more robust than these. And I have these cute little heat sinks that go just like that to carry away the heat. You can see they have little fins on the back. Isn't that cute? Yeah. But actually, I think you can buy these on Mauser and DigiKey. If I can look up the part number, I'll put it up on the screen when I'm editing the video. And I also have, we're going to replace these pots with some 10-turn pots. And these ones are going to mount, if I can get one to come out. All right. They're going to mount right in place, kind of drop-in replacement right here. And you can see how they had these bent down already to be able to access that pot. So it's going to be a drop-in replacement, 10-turn pot. That'll be give us a lot better control over adjusting the bias. and this thing will be ready to test. So let me get that replaced, and as we did on the 400 series, and I'm going to replace these 200 microfarad 6.3 volts with these 100 microfarad 16 volt bipolar capacitors. And those have to do with this little filter network right here that goes on your negative feedback line, just like I did on the other amp. So let me get those couple things replaced. All right, so let's go ahead and replace all these transistors in here. So yeah, you can see there's quite a few of them. There's 24 of them. And since this is the full complementary version of the amplifier, half of them are going to be NPN, the other half are going to be PNP. Looking at the schematic here, you can see where 5 of these on each side are the actual output transistors, and then 2 of them are the drivers, and they're the same transistor. So it's this and this are the same transistor. That's how they're doing it on this. And on here, this top row, these are actually the driver transistors, and then all the ones in the bottom, those are your outputs. If you look at the numbers, you know, they kind of mess around with, you know, some of the numbers here, but you can kind of tell what they are sometimes, but not always. For instance, if we look at this one here, let's see if I can zoom you in close enough to actually see it. See how that one says DB15025? Well, that's actually an MJ15025. And you can also use the MJ21195 or the MJ21196. There's a whole series of MJs that are basically the same as one another. They're very similar. So the 21195 and 21196, and I think there's a 21193 and 21194. There's about 4 or 5 different series like that, and they're all made, you know, by Motorola or by ON Semiconductor, however you want to word it, and they're mostly interchangeable. There are some slight differences between them, but for the most part, they're all 250 watt power transistors. Some of them, there's a couple of the series that are a little lower power rating. There's some that are 180 watt, something like that. They're all pretty similar. The good replacements for these that are available right now is the MJ21195 and MJ21196. Actually Dave purchased these. He found them, and he bought them from White Oak Audio, and as it turns out, they were a little bit less expensive than Mouser and DigiKey, so we went with them. These are going to cost you anywhere between $6 and $8 a piece, depending where you buy them from and what's available and what isn't. And the higher end of that price is Mouser and DigiKey. They're $7 and some change, almost $8 a piece. So you can times that by all of that, and we'll give you an idea of what you're going to pay for a set of these if you need them. Now, the problem is some of these older transistors may not be cross-compatible, drop-in compatible with these as far as mixing and matching. In other words, a whole set of these will do the same thing as the whole set of these, but what I would not do is replace, you know, pull one transistor out of this older type and replace it with one of these. Because what can happen is if the characteristics are not close enough, you could have one transistor hog up all the current because the VBE and certain things like that, the gain, some things may be a little bit different, and it will be beyond what these emitter resistors can compensate for. So my recommendation is, if you have a couple of bad transistors, replace the whole set. Make the investment. You'll do it once and you won't have to do it again. Unless you do something really stupid with this amp, you're not going to burn out these new transistors once you put them in. So think of it as an investment for the future. At least that's my thought on it. That's why I'm going to do this. Whoever buys this amp is going to get something that's going to last them a really long time. So to remove them, it's pretty easy. These ones are all socketed. So we can actually, it helps to have a long 1/4-inch nut driver like this. You can use a small one or a socket, but you'll see that these heat sinks are pretty long. And I'll back you out of here. And you can see you're kind of, you know, it's kind of, you're going at an angle. So if you have a longer one of these, it's going to be a little bit easier to deal with. So the way I take these out is I remove the 2 screws, and I should have gotten them out before I started this clip, shouldn't I? I have a long pair of needle nose pliers, and I just kind of go in there like this, and I grab hold of them around the camera, and I just pull straight out, and they pop right out. And you can see these are using those really good quality sill pads, so they can probably be reused. The only reason that if these are originals that I would replace them, which since I got a set of them with these transistors, I'll probably do it, is that sometimes if you tighten these too hard, you can see how they'll crease. You see how there's a little crease around there? I don't know if you can or not. See how there's kind of a little bit of a crease around there? I've seen the edge of these transistors actually cut through that, and you can sometimes short these to the chassis. So you got to be careful. And reusing them will probably be okay on this one, because these ones actually look to be, I don't think these are original sill pads from this. They might be, but I think the original ones that used sill pads like this, they used like a red or a clay colored one instead of these gray ones. But those of you who work with these more, you know, you might be able to correct me on that. Long story short, I have new ones. They were purchased with the transistors, so most likely I'm just going to replace them. And you can see these ones are really high quality. They're pretty thick. But these are the new Bergquist ones, and they are, you know, a name brand, high quality sill pad. It looks like they are the same as the ones that I'm removing. That's what makes me think that these were not originally with the amp. These were replaced at a later date. So you can see here's a new one. Here's the old one. You can see it's kind of worn a little bit and squished in, but these, I think these were really good. But you can see that little crease in there, and you can see the little crease in here. So, yep, we're getting new ones. Now, a couple other notes about replacing these. Before I really get going on this, I marked each row. So all this row is NPN, this row is PNP, and you can see I have the letters NPN, PNP. So I just don't get confused in the middle of this, because it's kind of monotonous going through this. The other thing I'm going to do is I'm just going to roughly spot check these with a transistor checker. I'm not going to put them on a curve tracer yet, or a transistor analyzer, or anything like that. I'm just going to do a go, no-go test on each one, because any of these that are reading still not shorted, I'll put them aside, and then I will test them. See, this one's a good one. You can see it's all right. This one's in good condition, at least from what we can see. So this one I'll put to the side, and then it'll go on the transistor analyzer at some point in time. And if they're good, I'll either save them or I'll put them up for sale, because they're good used transistors. Some people don't like using used transistors, but believe it or not, if these ones are still in good condition and they can operate under full current on a transistor analyzer, they're good to use. They could last a very long time, and they could bail you out of some having to buy all these if you ever wanted to go that route. I'd rather spend a premium for one or two of these than spend hundreds of dollars on a whole new set of the other ones. So, you know, it's all a matter of how you look at it. But that's what I'm going to do. Okay, so the the MJ21196 is the NPN transistor, and the MJ21195 is the PNP transistor. So we're working on the NPN section right now. So I'm just going to replace those. And all we're going to do is you don't use grease or anything with these sill pads. That's the beauty of them. You don't have to mess around with, putting all that goop on there. I like these. And they actually have a better thermal transfer than the grease. And the sockets are attached to the chassis, so you just kind of plug them in like this and put the screws back in, and it just takes a minute. Whereas when you have to go with the mica pads and the grease and the screws and the insulator things, what a pain. But these ones are real easy. It's as simple as that. I'm going to do this 23 more times, right? And this will be all done. So the biggest thing is just not to get the screw cross-threaded in the socket. It should thread down in very easily when you do this. And that's it. Just snug it up. Not real tight. If this starts curling up on you, you've tightened it too much. But you should just feel the screw bottom out and then just give it maybe an 1/8 or 16th of a turn, and that's it. And there you have it. So I'm going to do all the rest of these the same way, and the transistors will be done. It's that simple. Okay, so all the transistors have been replaced. They have nice new sill pads on them, and they're mounted properly. And here's the damage. Not as bad as I thought. So these were all good transistors, at least just on a small, Peak Atlas transistor tester. They were not tested under load. I'll get more into that here in a minute. But these are the failed ones that I found, and the worst ones were on the right channel here, this channel on this side over here. So this channel had the most bad transistors. This one just had some, well, you'll see in a minute. So first of all, the worst ones, we had a couple of them, 4 of them, that had, 3 of them that were dead shorted. So we had this one was emitter base collector short all the way around, and then these 2 were just emitter collector shorts. And they were NPN and PNP, I believe. Yes. So those were bad. This one had really low VBE, so much so that the tester actually thought it was a germanium transistor. That's not necessarily a terrible bad thing because there was no leakage with the test current and everything. So this is probably still technically a good transistor, but it had much lower VBE than these other ones. These are all running somewhere around 550 to 570 millivolts with very low signal on them, of course. This one was closer to around 500 millivolts. So of course the testers thought it was a germanium transistor. These 2 just had really, really low gain. Again, some of these transistors brand new out of the box will have low gain. So these ones were only like an HFE of 10 and 12. All the rest of them are anywhere from 25 to the PNP ones can be up to 70. So again, these are still probably good transistors, but just had a lot lower gain. And that could be because they're getting tired. It could be that that's how they were from the factory. If you test every one of these, they're all going to be slightly different. It is a fool's errand to try to match output transistors. Number one, it's really not necessary. Number 2, if you have a full complementary amplifier, almost always the PNP transistors will just by their nature have higher gain than the NPNs. So again, it's just not something you worry about. The way these things operate, the gain isn't a huge deal on them, which is why I say these would probably still work. Just giving you all a few pointers. All of the know-it-alls out there that says they know all that, well, I'm happy for you. I'm just trying to help some of the folks out there that don't know some of these things. So anyway, with that said, we're about to the point where we can start putting this together and giving it a first power up and just see how it works. Now, one last note on these transistors, and this is what I was going to talk about later. If you connect one of these small, I don't care if you use this, I don't care if you use the more expensive version of this, what is it, the 75, that you can make little pictures on your computer monitor with it, or if you use one of those Chinese cheapo ones, they all do the same thing. And while they do at least make sure the transistor can conduct, forward biased signal, you can see what this tells you, and we'll go through this. It tells you what it is. It tells you the pin out and the gain. So you see this one has an HFE of 40, which is good. It's testing it at only 2.5 milliamps of collector current. That's very important. Your forward voltage drop, your VBE, is 560 millivolts. That's pretty normal for these. The test current for your base current is 4.85 milliamps. And this is your leakage current, which it should always be 0 on a silicon transistor. And it could be a very small amount, in the microamps usually, when you're dealing with a germanium transistor, because most of those have a little bit of leakage in them. The problem is the test voltage on this thing uses a 12 volt, MN21 battery. And that's a stretch even saying that it's going to apply 12 volts across this. It's really only applying a few volts test voltage on it. Where these were designed to operate, at least these new ones here, and even these, in the hundreds of volts, 100 to 250 volts, depending on the transistor. In addition, these transistors can dissipate up to 200, 180 to 250 watts, again, depending on which transistor we're talking about. Like these ones that we just put in, they're at 250 volt maximum voltage collector emitter for the reverse breakdown. And the dissipation, they can dissipate up to 250 watts of heat when properly attached to a heat sink. So in the real world, you would never see signals like this puts on this. So this, again, this will tell you if the transistor conducts. It won't tell you if the transistor functions up to spec. Why is that important? Well, let me see if I can find it again. Okay, so here's a few TO3 type transistors that have the caps removed from them. See that? And for instance, this is, I believe, an original Motorola 2N3055, which is actually a lower power version of these. These are only good for 115 watts. Their breakdown voltage is about 60 volts. But anyway, you can see the big heat spreader plate on these. This is your modern Chinese TO3. They connect the die directly to the plate, to the case. They don't have a heat spreader plate like this. Now, what I really want you to look at, though, is, see this little wire here? This tiny little wire? And you see on this one, it's even thinner. It's a little teeny. This one has actually, these both have come off. See that? These are called your bonding wires. They typically would be spot welded to here and to here, just like this. And those go to the pins. All right. Now, what will happen sometimes, why a transistor will go, a couple things can happen. If you have a dead short, then something on the die actually shorts out. But you can also have these bonding wires, when they get really hot, when they're conducting, I mean, it's a lot of power going, you're 250 volts at amps of current. These are going to get hot. As they get hot, they could droop down, and you can see what can happen here. You could actually have this short to this. A lot of times, if you see a shorted transistor, it could be that this wire is shorted. Let's decap one of these shorted ones if we can find it. So here's one with an emitter collector short. Let's see if we can pop the top off this. I don't know if I can. Let me see what I can do. Okay, so after abusing this thing, I was able to get it apart. This one has an emitter collector short. Now you can tell the difference between the base and the emitter because on these heavier, higher power transistors, if you notice, the emitter has two bonding wires. See them? One here and one here. And the base, since it doesn't carry as much current, has one bonding wire going to the pin. And you can see how much thicker, when you compare this one, you look at the wires, see them? And then you look at the wires on this one, how much thicker they are. Big difference. And you can see where the short took place on this one. So for this one, you can see that little stain right there. I don't know if you can see the crap stain. So the die actually shorted to the case right here. This is the actual transistor die. And you see how much larger the die is on this one than on these. These are 2N3055 type transistors. So they're 115 watt. And you see how this one's a 250 watt, has a bigger die. And what can happen on these sometimes is these will heat up. As they heat up, they'll droop down, and you can actually have a short on the bonding wire to the case. And what will happen is from excessive current, these bonding wires will get soft, and they'll eventually burn. So this is why you can't, some of these transistors sometimes when they don't dead short like this, they may still test good. And if they test good with this, as soon as you put any real kind of current or anything to it, the transistor will let go. The reason I'm giving you this big talk is because you got to kind of watch when you go online and buy transistors, the power transistors that were pulled out of a circuit. And it's not as big of an issue with little signal transistors, but these big power transistors, you got to be careful. If they haven't been properly tested on, for instance, like the curve tracer over here, the 576, or better yet, the triplet transistor analyzer, those can both put high current and high voltage onto the transistor and test it under load. If it passes that test, chances are the transistor will work just as good as a new one. But if it's going to go bad, it will go bad during that test. That'll end it. So I just thought you'd be interested in knowing that. And there you go. So let's get this thing put together. Okay, so here is where we are so far. Everything's done except these last four transistors. You can see I have the one out. I just kind of marked the holes. And the problem with these is to use these transistors in here, you have to twist the pins around. And what will happen is the only way you can do it is if you face the transistor this way, the back of the transistor, and then bend the center pin backwards, which is going to come in contact with your heatsink. So what I'm going to do is I have some little teeny tiny adapter boards, and they adapt a TO5 case like this to a TO126. And it'll just sit right on top like this. Unfortunately, I don't have any in stock, so I had to order some more. And they're coming from JLC PCB, which is who has the Gerbers for them. Why do I use JLC? Well, probably because that was the first place I used, and I've just been using it ever since. I know a lot of people use that PCB way, and when I originally had my contact info on my YouTube channel, I got a whole bunch of people wanting me to advertise and sell their crap and all that, and that's why I got rid of it. Along with the old lady who was a wealthy billionaire or whatever and wanted to transfer all her money to me and all, because I'm some long lost 25th cousin. Yeah, you get sick of that after a while. I get enough of that as it is. I don't need that on my YouTube channel. So, as I digress. So when those little adapters come in, which should be about 3 or 4 more days, I'll get these mounted up. We'll come back and the amp will be ready for testing, and that will be the video of actually seeing how this mess actually works. So until next time, I hate to leave this a cliffhanger with you all, but I wish you all peace, joy, happiness, and good health in your lives. And we'll see between this and the surgery I got to get done. We'll see how long it takes. But I hope in the next week and a half or so, I'll get this done and off the bench. All right, everybody. Until then, we'll see you later. Take care. Bye-bye.